Can you please describe the procedure of an organic synthesis to the class? So to begin our experiment, we're going to have a flat bottom distillation flask. We're going to add about 3 pellets of NaOH, 5 ml of N95% ethanol, a stir bead, and 0.5 grams of 2-naphthol. After that, we're going to continue setting up our reflux system. I have a simple drawing behind me of it. So basically we have our flask, we're going to put it onto a hot plate. We're going to add a condenser, that pole on top. We're going to want to make sure to have the flask clamped to a support system along with the condenser clamped. Then we're going to connect tubing to it, to this little thing sticking out here and this little thing. This one is going to be a water in source, and then this one will be water out, which will just go straight to waste. After we have all of that set up, we're going to boil our system for about 15 minutes. After everything has dissolved in there, we're going to add 1-iodobutane to it by taking off the condenser, then using a digital pipette to add that in there. Then we're going to change out the condenser, put a new one on there, and then boil the system again for another 1 to 1.5 hours. Near the end of our experiment, we're going to take a little sample from our things. So take the condenser off, take a little sample, and then do a TLC experiment and leave this to continue the reaction. After the reaction is actually done, we're going to do a workup experiment. So basically all you have to do is have a beaker ready with a couple ice cubes in there, and then we're going to pour our mixture over top of the ice cubes. Then we leave them in there in the beaker to melt, the ice cubes to melt. And then after that, we should have crystals formed, and we will just perform a suction filtration on that. So I mentioned how to do that earlier, but basically it's just an Erlenmeyer flask. You have your Buchner funnel on top with your filter paper and a suction source. You pour your mixture into there and leave it until all of the crystals are dry on top. Yeah. Okay, yeah. Now, we actually tried this experiment the other day in our class, and we got these results. Would you be able to analyze our product for us? So to begin assessing our compound, we're going to look at TLC plates. TLC plates can be used to do a lot of different things, but in this case, I'm going to use it to assess the purity. So in a TLC plate, you'll have a lane on the left, the right, and a co-spot in the middle. So left, right, co-spot. On the left, you'll have one compound, say A, and on the right, you'll have one compound, say B, and then in the middle, you're going to have a spot for both A and B. Each compound will have its own distance it travels up the plate. So on the left, ideally, there should only be one spot. On the right, there should be one spot. In the middle, there should be two corresponding to compound A and B. But I'm going to show you the TLC from the actual lab right here. And then right here, we have just a simplified drawing of the TLC so I can compare them with you. So as we can see right here on the right, there is 2 spots in each lane, which suggests that there has been contamination, because this on the left that I've drawn right here is how a TLC plate should look. 1 spot, 2 spots in the middle, but this one has 2 spots in each lane, suggesting the contamination. Okay, and so that means our compounds will not be pure. Next, we're going to look at the percent recovery of our product. So I have it drawn right back here. We are going to have our final 2-butoxynaphthalene mass over top of our starting 2-naphthol mass. We're going to multiply that by 100, and that should give us our percent recovery. So as you can see, I got a 55.78% recovery, which means that our system maybe wasn't completely efficient just because we lost about 45% of our starting material. So basically, a percent recovery will compare what you start with to what you finish with and how much you have recovered from that. And yeah, so last we're going to look at our IR spectrum, which I have right here, the IR spectrum from our experiment itself. As you can see, there's a few peaks right here at about the 3000 mark. And then I have here a literature value of 2-butoxynaphthalene. And these signals actually do seem to be about exactly identical. Down here, there's like values, the literature values of what they should be. And I compared it to this one, and they're literally pretty much identical, just about like 3 marks off or so. The only difference between the two is that the literature value is stronger, has a stronger reading, but that could just be due to them using a larger sample, because more molecules will make a bigger reaction, like a bigger reading. And yeah, so there's no indication of any unwanted functional groups in there. It appears to just be everything that there should be for 2-butoxynaphthalene. What kind of mechanism do you think it underwent, SN1 or SN2? So in the synthesis of 2-butoxynaphthalene, our system underwent an SN2 mechanism. In an SN2 mechanism, the nucleophile attacks the substrate simultaneously as the leaving group leaves. For this to occur, the nucleophile has to be strong enough to attack the carbon. A strong nucleophile is something that is charged and polar. We used hydroxide, which is both strong and polar. The nucleophile also has to be readily accessible to the carbon center, which in our case it is because it's simply sticking right off of 2-naphthol. Iodobutane is our substrate, and it is not a bulky molecule, which will make it more reactive than if it were a bulky molecule. It is also a primary substrate, which will just furthermore make it favor a SN2 mechanism. In an SN2 reaction, the pair of electrons on our nucleophile, which in our case is hydroxide, will attack the carbon center. The proton in our protic solvent can act as a hydrogen bond donor to our nucleophile, rendering its nucleophilicity useless. Because of this, we need a polar solvent, but we did use ethanol. So ethanol is polar. So this will further support our evidence that an SN2 reaction occurred. But we haven't talked much about an SN1 reaction, so let's just go a little bit over that to further our understanding. In an SN1 reaction, the leaving group will leave prior to the nucleophile attacking the carbocation. You usually need a nucleophile that is weaker in this case, otherwise the nucleophile will attack the carbocation prior to the leaving group leaving. But as we stated earlier, we used a strong nucleophile, so our reaction does not fit the characteristics that are necessary for an SN1 reaction.